Okay, here is our last note set in the reverb unit, Unit 4, RVB for reverb. And we're going to be talking about something called feedback delay networks. And this is um, uh, basically a generalization of what Schroeder put into place. And so my presentation is mainly following Gardner's nice review of reverb algorithms, the chapter 3 in this edited book. I've talked about that before. Some coverage in the DASP book, and also this 50 years of artificial reverb review paper um, gives some details on this, not a lot of depth, but it certainly points you to all the appropriate literature that at least had come out since 2000 or up to 2012. So we've only got 9 slides on this, so we're not going very deep. I needed to limit this just to fit everything into a 1 semester course because there's other topics that we want to talk about. We've got one main unit left after this, and that's A to D converters and D to A converters. So if you're interested in this in more detail, I've given you the basics of it, and then enough for you to chase the more detailed papers that you can find here, and also Gardner will tell you about that. And also DeToro has a reverb paper and talks about this there as well. We've mentioned DeToro's work in previous videos. Okay, so we start with something called unitary multi-channel networks. So remember, Schroeder's ideas were introduced at the beginning of the 1960s. Digital signal processing was really young then. It was coming out of some ideas in the 1950s, but really it was through the 1960s and into the early 1970s where a lot of the foundational theory of DSP was being developed. And so people were looking at lots of new mathematical ways of thinking about discrete time filters. And so one of those ways that was just being looked at for general views of discrete time processing was something called unitary multi-channel networks. And so that was floating around in the in the theoretical developments, not necessarily focused on reverb at all. It was just a generalization of the idea of all pass filters, which also were just kind of being explored during that time. So that's kind of how research in general, but particularly in DSP, kind of developed. People started with very straightforward ideas and then just kept applying more and more mathematical concepts to learn and understand more elaborate ways of doing the processing and understanding what was going on, coming up with nice design approaches. So let's think about an all-pass filter. An all-pass filter has a flat frequency response magnitude. So if we think about the output of that being y and the input of that being x, we can use Parseval's theorem to say, well, if we sum the output samples in the time domain, square them and add them all up, we can figure out what that is represented by in the frequency domain. And so that would be Parseval's theorem. So this product gives us the magnitude squared of the output signal. So we take the magnitude squared of that in the frequency domain, square it, and integrate minus pi to pi. And Parseval's theorem says squaring and integrating in the frequency domain is equal to squaring and summing in the time domain. Then we say, well, since this is constant for an all-pass filter, and we can really set it to be equal to 1, that's kind of the most obvious scenario for an all-pass filter, that goes away and we're left with just the x. And so if we sum Or if we integrate the square of that, Parseval's theorem again tells us that's equal to the sum of the squares. So look, it maintains energy. That's a measure of the output energy, and that is a measure of the input energy. So an all-pass filter retains the energy of the input to the output. Okay, so let's generalize that. And one of the things that people were looking at were multi-channel filters. How do we take multiple inputs into one interconnected system to create multiple outputs? So we looked at that in the state space viewpoint, and we'll revisit state space when we get to the end of this note set, just briefly. So this idea of a multi-channel network, and network is just a discrete set of discrete time filtering blocks that take multiple inputs and map them dynamically into multiple outputs. Okay, so if we want to generalize this idea, we should say that we're going to preserve the total energy of all possible inputs. And we're going to, instead of calling that an all-pass filter, we're going to call it unitary. And so this was something that was developed in general, and then people recognized that once people started using all-pass filters to simulate or emulate reverbs, now we can take this general idea of a unitary multi-channel network and apply it to reverb. And that's what this feedback delay network approach, that's where it comes from. So here's, again, not reverb specific. This is the general definition of a unitary feedback system. So we have a vector x at some instant of time. So I think, I borrowed this from reference 1. We really should think of that as a vector at each instant of time, and the output is a vector at each instant of time. And so then we can think of a matrix or multi-channel system. So this vector is added to this vector and goes through this multi-channel transfer function. So typically same number of inputs and outputs, although I suppose it doesn't necessarily have to have that in general, but for a unitary feedback system, it does. And then this part, in addition to being the output vector, goes into here. Again, a multi-channel transfer function that tells how that gets mapped to the thing that becomes the feedback signal. So we can think of these transfer functions. Notice the symbology that I've used: bold, uppercase, non-italic. That's indicating that these would be matrix functions of Z. So you have a matrix. Each element in that is going to be some function of Z, and that's going to be showing the transfer function from one input to a particular output. But remember, let me just rewrite this here. If this is, say, U1, that would be a matrix of Z, and let's call this here V. Let's call that matrix V. We would think about this vector V1, V2, all the way down to Vn, and then this output here Y. So we would have Y1, Y2, all the way down to Yn. And we would be thinking about Y1 is a bunch of different transfer functions. We'll call this U11 of Z all the way out to U1n of Z. Remember, matrix times vector multiplication. This V1 is going to multiply this, the V2 is going to multiply here, the Vn is going to multiply by here, and you add them all up. So all of the inputs get mapped through some combination, linear combination of those, into the first output, and same thing for the second, and so on. So that's the idea. And we can specify for reverb systems a specialization of this idea. So in general, these things would have to have special conditions on them, and they would be what are called unitary matrices. And each of U1 and U2 would describe a unitary system, and when you connect them into a feedback system like this, they still, as a whole, describe a unitary system. So here's our special case. We're going to have a bunch of delays with M1, M2, Mn being whatever we want. Those would be positive integers. We have a matrix A here, and we say that the output of these delays, we'll call them S1, S2, down to Sn. We can write that as a vector at time n. So this has dynamics. That's the U1 of Z. This has no Z's in it, so it's no dynamics, but it is still a feedback system, just consisting of coefficients, no dynamics. So this would consist or comprise the U2 of Z transfer function. And so here I'm denoting whatever this vector is, gets multiplied by this matrix A to create whatever that collection of signals is that gets fed back and added to the input. So that's the idea. Notice that in the diagram, we're evoking this the action of this matrix multiplication by having these arrows go up to columns. So remember, on the previous slide, I just showed you how a vector here getting multiplied by A, that this first element multiplies here, and then the second element multiplies here to get the results coming out of this line. But every one of these output lines, the first element here interacts with the coefficient in the first column. So that kind of makes sense showing it like this. So that's just evoking that idea. But in reality, mathematically, it's just matrix times vector multiplication. Now, we said that these two things have to be unitary in order for the whole unitary feedback system to be unitary. Well, delays, they are obviously unitary. You're just shifting in time the signal that goes into them. So that retains the energy. That's one way to look at it. But also, if we were to find the frequency response of that, well, it becomes e to the minus j omega m1. Take the magnitude, that it's equal to 1. So we see that each of those is all pass. So just unitary is just a generalization of that idea. Okay, so we've got this part handled. That's a very simple unitary system. And that's where the dynamics will be in this reverb system. What about this matrix A? We need to have some conditions on it. Can't just be any old matrix. Turns out that there's some mathematics that comes in, and there's a reason that we use the name unitary. So in mathematics, the concept of a unitary matrix, okay, they might have something. Generally, they use a Hermitian transpose here, which involves conjugation and transposition, but we're just borrowing that concept here. So matrix A is unitary if A transpose A is equal to A transpose, and each of those products gives you the identity matrix. So in other words, to invert A, all you have to do is transpose it. It's a special class of matrices, and they're called unitary, and they lead to this unitary multi-channel network view. So this matrix A plays the role of U2 of Z, although there is no Z dependence. So it's just like a coefficient multiplication in a regular filter. Turns out, if we analyze this, because this is unitary and this is unitary, the poles will end up being on the unit circle. So that's an important thing to remember. But that's not what we want for reverb. But this is where we're starting. So remember, this was a generalized idea, unitary multi-channel system that was being developed for a bunch of different applications and concepts. And the reverb people looked at that and said, I can find a specialized one that I'm going to use. It's not quite there yet, but we're going to start there. So let's see what really motivated people in the reverb world to get into this. A very interesting observation from Mohrer's paper. So one of the things I really like to see in research is when people just kind of make observations in their paper to kind of just think out loud and ponder. And so one of the things that Moore said in his paper on what about this reverb business or something like that is he said, if you look at a realistic room's impulse response, we can really just look at that as starting with some sort of stationary white noise. Now, that's some terminology coming out of probability theory, so let's not worry about it too much. It's kind of what you think about when you think about an actual random noise. So you start with a random noise signal and you put an exponential decay on it. And he said that would actually, if you did that, that would give a pretty good impulse response for a realistic room. Now, you have no way of making that to make it sound like a particular room, but it would sound like a reasonable reverb. That was an interesting observation. But then he said, yeah, but can't really do that because I don't know how I would implement that in any other way than making it this way and getting a very long impulse response and then using that as the impulse response in a convolution reverb. And so if you're going to do that, why not just measure an actual room and then implement it? You'd be better off. So he kind of said, gee, that's kind of interesting, but it's not really taking me anywhere. Well, down the road, another researcher, Jot, along with Jot was a PhD student at the time, working with his PhD advisor. They were working on these ideas of uniform feedback networks, just generally and arbitrarily, developing some of the theory of those. And one of the things that they found was that you could use these unitary feedback loops or feedback networks to create what they called lossless prototypes. So those were those lossless systems that the total energy in equals the total energy out. And if you looked at the impulse responses of those things, this is one thing they recognized. They looked like stationary white noise. So they kind of stumbled upon a new way to generate fictitious stationary white noise. Now, if you're still wondering, what is all this stationary white noise stuff? We're going to be getting into the probabilistic view of that in the next unit. So go check that out and then come back here if you've got questions. So that's a quote right out of Gardner's paper telling us what Jot was thinking about. Again, a quote right out of Gardner's paper saying what Jot and his advisor did. They started realizing that this connected back to reverb. So they weren't really interested in reverb, but it was an interesting application of some of the more abstract theory they were developing. And so they started looking at putting losses to model the absorption of walls. And they started with a suitable lossless prototype, stationary white noise, and by putting these losses, these absorptive losses in there, they were imparting this exponential decay. But they had a nice way to implement this that was not just creating a white noise, putting an exponential decay on it, and then doing convolution reverb with that. They had this feedback network that they could work with. So the way that you can accomplish that, one way is that back in that system, so back here, each one of these delay boxes gets hit with a coefficient whose magnitude is going to be less than 1. And so that's what they did. They show it as k sub I less than 1, but technically it could be magnitude less than 1, but we might normally just keep these to be all positive things. And it doesn't matter whether you put that after or before, it doesn't really matter. So now how do we choose those things? So we choose the k sub i's so that the logarithm of the gain is proportional to the length of the delay. So that puts a connection between the k sub I and the m sub I. So that's going to give us some sort of decay that is connected to the amount of delay that's happening in that leg. So we're not going into all the details here. I'm just kind of reporting on some observations that led to this. So now you could put those in here as I showed. So we could just insert those k sub i's here. But remember, we said the thing that comes through here goes up and gets multiplied by each of those things to form each of the individual outputs, or a part of each of those individual outputs. So if I'm putting in a multiplier here, why can't I just drag that up here and change each one of these A's by, so the A11 would be A11 times K1. A21 gets replaced by A21 times K1, and so on. So everything in here gets multiplied by K1. Everything here gets multiplied by K2, and so on and so on. And so now we can do something that will implement something that will sound like a reverb. So Jot's PhD work, in addition to a bunch of just generic work on unitary multi-channel feedback networks, proposed a reverberator. And it had two very important characteristics that we can now achieve easily with this new viewpoint. So Jot used this new theoretical construct, reached out, found this Moore comment, decided there is a good application area for my new esoteric views, and worked that out and published a couple papers, even though that wasn't his main focus. So what can Jot's approach do? We can get arbitrary time and frequency density. So remember, that was the stuff that was a challenge to get. But we can also get absence of tonal coloration in the late decay. That's the all-pass nature, or at least the very closely spaced modes that the ear hears as essentially perceptually a flat frequency response. But on top of that, we can also get frequency-dependent reverb time. We saw a plot of the energy decay relief, I think, maybe. I can't remember what that stood for or what that was. But it was that time frequency plot of the energy decaying in a room, and it showed that the reverb time was a function of frequency for an actual room. So we can do that. And so that's the idea. So Jot started here with A being a unitary matrix. And then A matrix is formed from a unitary matrix with each column multiplied by an absorption gain. So we've already modified these. So the A is no longer strictly unitary. It starts as unitary, then we put in our coefficients as necessary or as desired. And then also included a direct path and could put in some stuff to handle the early echo stuff as well, although we're not showing that here. So here is JOT's feedback delay network reverb. This has got the absorption coefficients in it. And then we weight together those different outputs together. And we include a weight on the input through there. And if we think about this, this looks an awful lot like a state space representation. So one of the nice things about state space is it handles multiple inputs and outputs. So we can think about this part of the system as being characterized through the state space. In fact, maybe we don't even get the C's that might show up in the output. So we can characterize that in state space view. So we've got A matrix here. We've got a D of Z matrix here. And if we write this out, if we look at this carefully, this is how we think about this in state space view. So this is the state model. So here's the state, just written in the Z domain. So the D of Z interacting with the A gives us the matrix that maps S of Z to S of Z. And then we have our input. And then we have our output form. So this is a little generalization of what we saw. And I don't go through the details. We talked about this, that we could get a transfer function view for a single output formed this way. This ends up being a single output here. And we can find the transfer function from X to Y. So we can think about it in state space view. We can think about it in transfer function view. So if you've studied state space, you know where this idea comes from. And we looked at that back in our Unit 1 coverage of state space, so you should know where that comes from. But now we can think about this in a variety of different ways. We have the feedback network view, we have the state space view, we have the transfer function view, and so on. From this transfer function view, we can look to see this is a function of Z. Well, this whole thing is a function of Z. Look at the denominator of that. Well, it turns out to be set by the determinant of this matrix right here, setting it equal to 0. So it's the roots of that. And so we can find the poles of that. And if we were to go through those steps, we would find out that with the gains set according to this rule, all the poles of this system will end up being on a radius of gamma. So those are our absorption. We pick a gamma to make this case of I from the desired radius that we want our poles to be at. So a lot of fundamental interconnections between these different views. Now, here's the thing. How do we choose this? What are we trying to strive for? We want to make these absorptive losses frequency dependent. We talked about that. So what we have already, on the previous slide, picking everything that way, the absorptive losses were not frequency dependent. So now we can throw in a transfer function in each little path. So we would put one in here, we'd put one in here, one in here. Remember, we've already got the case of I's interacting in the A matrix. So now we're putting in things that will provide a different attenuations based upon frequency response. So now we throw that in there. And it turns out that how do we design these things? Well, we design those based upon our desired frequency-dependent reverb time. So you can go measure that energy decay function, I think, whatever it was we called it. We can go measure that for a particular room or craft one for a particular room that we would like to be trying to mimic. and then use that to design our frequency response. And we'd have to use some frequency or some filter design routines to try to come up with the right frequency design for that. We talked about using things like Prony and Steiglitz-McBride and things like that. So those would be approaches that we could use to achieve a desired frequency response. So now we stick that in there, and what we find out is that, well, that gives us the right reverb times that we want, but it will also make the frequency response no longer flat. So that's not good. So now suddenly, if we just left it like that, the ear would hear certain frequencies being weaker or stronger than other ones, and we don't want that. So now we need to adjust that. And so it turns out that the frequency response envelope is proportional to the reverberation time. So we know that it's no longer flat, but we also know exactly how not flat it is. And so now we can fix it. And again, I'm skipping over all the details of this. You can go read Jott's paper about this. But what comes out of Jott's paper is we know that this, since it now is proportional to the reverberation time at all frequencies, we need to adjust that. So if we put this in, then we will have compensated for that. And so here's the final structure. So remember, we've got the K's in here, chosen using the little formula that we had before. We put in frequency responses here, designed according to those, based upon the measured frequency response or reverb time frequency dependence. And then we pick the T from the formula on the previous slide to correct that. So now we get the desired reverb time and we get a nice flat frequency response. And this is Jott's FDN reverberator. And now I am referring to this 2012 paper, which is a really nice review of 50 years of work in reverberation. And they say that even in 2012, this approach, although it's been revised and finessed and tweaked and pushed further, but this Jott's approach with some new developments, but it's still FDN, remains even today, 2012, state-of-the-art reverb method. Now, remember back a few note sets in this unit, I pointed out the Big Sky stomp box. It does reverb, and you can see the choices here of the types of reverb, and the user gets to set various parameters and so forth beyond what would be the default values. And I pointed that out. I think this link is still good. At that link, they say they used feedback delay networks. So that's still even today. So, over a decade later, this is still the approach. So we only did 9 slides. If you are interested in becoming a reverb expert, you got to go off to this paper and look into the research for FDN. There's a lot there, and stuff has still come out since 2012. But that's your roadmap. Didn't want to go into all the details because not everybody wants to become a reverb expert. But if that's the direction you want to go, I've laid out the map to how to get there. All right, that is the end of our Unit 4 on reverb. And pretty interesting stuff. Now, in the next unit, as I said, we're going to go into analog to digital conversion and digital to analog conversion. So that's the front and back end of any digital signal processing, digital audio system. So when I first taught this course, I covered those ideas first. But I got the sense that students were like, I want to get into the audio stuff right away. So I switched it up the next time I taught it and put this stuff at the end. But in reality, as we'll see, the ADC and the DAC stuff is really the most important stuff for any digital audio processing stuff. If you don't do either of those things right, no matter what you do in your algorithm, it's going to sound bad. So check it out. Hope to see you in the next unit.